Shankar, and he's going to give us a gentle introduction, I think, to parametrization.
That was awful.
Right. Well, thank you. I realize that most of you, this is not the focus of your work, but so in that case, I'm going to really go, I hope, a fairly elementary level. But if there's things I'm saying that you don't understand, please interrupt and stop me. So let's start with a plot of sea surface temperature from two different resolutions of an ocean model. This is the South Africa, and so we're looking at the Southern Ocean here, and in the high resolution, which is 1/10 of a degree, this is the sea surface temperature on a particular day. And what you can see here is that there's a strong current coming down the southeast side of South Africa called the Agulhas current. And it comes round and it retroflects in this direction and goes back to the east here, joining what's known as the Antarctic circumpolar current, which is a strong current that goes all the way around the Earth at the high southern latitudes. As it does this, there are small disturbances, eddies we call them, mesoscale eddies, that are here, and there's instability going on all through the Antarctic circumpolar current. And there are also Agulhas rings, which come off here and actually then go northwest into the South Atlantic. This is an equivalent day from a simulation which has 1 degree horizontal resolution. And as you can see, that the field is absolutely smoothed out compared to what's going on here. And the reason for that is that in the ocean, the Rossby radius of deformation is much, much smaller than in the atmosphere. The ocean varies in its density from the surface to the bottom by about 3 or 4 parts per thousand. Whereas in the atmosphere, the density changes a lot more radically as you go up. That change in vertical density gradient means that the Rossby radius is much smaller in the ocean than the atmosphere. At this latitude in the ocean, the Rossby radius is on the order of a few tens of kilometers, maybe 40 to 50. Whereas in the atmosphere, the Rossby radius is on the order of about 1,000 kilometers or more. So in the ocean, these mesoscale eddies are the equivalent of highs and lows in the atmosphere. In an atmosphere model at 1 degree resolution, you are partially resolving those eddies, highs and lows. But in the ocean at 1 degree, there's absolutely no chance of resolving these mesoscale eddies, which in fact, if you look at a energy spectrum of observations in the ocean, these are the most energetic scales of motion in the ocean. And they are not resolved at all in a 1 degree model, which is the type of resolution that is used in climate models. So, the big question is, how are the effects of these eddies to be parameterized in this 1 degree model? So let me go over the equations that we solve in an ocean model. There is a usual form of the momentum equation. For u here is the horizontal velocity. So we have time rate of change plus a 3-dimensional advection of velocity, the Coriolis force, the pressure gradient, and then these two terms over here. And it's usually thought that the horizontal viscosity here is really a closure to make sure the suppressed noise in the model and to make sure it doesn't blow up. Whereas the vertical viscosity here is thought much more to represent physical processes. The wind blows on the surface of the ocean, creates a lot of turbulence in the upper mix layer, and that turbulence is driven down by vertical exchanges, which are much stronger in the upper ocean than when you get deeper in the ocean. So this is thought of as a physical process, this as something to control noise in the numerical model. In the vertical, we don't have any of the accelerations of dw dt, and we just assume hydrostatic balance. So the vertical pressure gradient is just proportional to the density. And in the ocean, the density is much higher than the atmosphere. So the vertical pressure increases much more strongly as you go down in the ocean than it does if you go up in the atmosphere. Seawater is deemed to be incompressible, so there's no d rho dt's in this equation. And if you have a control volume, what goes in on one side has either got to go out the other side, or it's got to go out in the vertical. So we have a three-dimensional continuity equation like this. And then there are equations for the temperature and the salinity. And we need these equations because the equation of state for density in the ocean is a function of pressure, temperature, and salinity. And it's actually quite a complicated function. It's somewhat nonlinear. But what happens is, where the temperatures are high, so in equatorial waters, the density is mostly controlled by changes in the temperature. In the high latitudes, where the temperatures are cold, the changes in density are actually mostly dictated by the changes in salinity. So there's a difference there between low and high latitudes about what of these two variables is dictating density. So temperature and salinity, again, both have these vertical components over here, which represent physical turbulence and a physical process. But in the early ocean models, in the horizontal, they had this Laplacian horizontal viscosity, diffusivity. Now, it was this was really then can be thought of as the representation of the unresolved scales in this equation. So this can see sort of like the u prime, theta prime bars is a parameterization of those unresolved scales. And those in the early models were in the horizontal. Now, it's been known actually for a long time, both by ocean observations and another way I'll talk about in a minute, that in the ocean, the mixing is far, far stronger along the isopycnals than across them. Isopycnals are what we call for surfaces of constant density. And observations suggest that if you put some dye in the ocean like this, that it mixes in along the density surfaces about 10 to the 7th times as strongly as it mixes across them. And the other way that we know this is that in the old school of oceanography, people would describe water masses in the ocean, and the reason that they could do that was because once a water mass gets buried in the deeper ocean, it changes its temperature and salinities very, very slowly. So in other words, you can follow a water mass as it's been advected around the ocean for hundreds, if not thousands of years. And people talk about, for instance, Mediterranean water, which is very saline water, comes out through the Gibraltar Straits, and you can see it as you go west in the Atlantic, and it starts to sink as its density to get to a neutral density. So the reason that those can be described as water masses is because mixing across density surfaces is very, very slow in the deep ocean. And it was been pointed out by several people, but especially by these two, that if you have horizontal mixing in your ocean model, where the coefficient is 10 to the 7 times the mixing you want across the isopycnals, that even when this angle is extremely small, you are having an amount of cross-isopycnal mixing which is proportional to your horizontal coefficient times the sine of this angle. So, unless you actually get mixing to be along the isopycnals, if you have it in the horizontal, you are introducing into the model much too much spurious cross-isopycnal mixing. And that's what happened in all the early ocean models. And you could not maintain, certainly deep water masses, nearly as long as you wanted to in the ocean models. So,
Can I
yes,
help you, Peter?
yes.
The naive question is, well, naive conclusion from what you said is, so we should use isopiconal vertical coordinate than geometrical vertical coordinate. Then seems the most of the problem will gone. Am I right or wrong? Or
If you there's two types of ocean model. One uses a depth coordinate. What Unichi is then saying is there's another one which uses density as a vertical coordinate. And if you put in del squared in a density coordinate, then you are doing this mixing along the density surfaces. So it makes that part easy. But there are many, many other disadvantages of using a density coordinate, which I don't have time to go into. And the bottom line is that the vast majority of large-scale models that are used for climate still use a depth coordinate, not a density one. So, but one of the big advantages of an isopycnal coordinate is that this horizontal mixing is automatically done
so
for
that
you.
may be a way to go, though it's not easy.
There are some. I think you earlier had a talk by Bob Hurlberg. He's been one of the guys who works on isopycnal models a lot. So there are some around, but still the large majority are.
Yeah,
dense.
that's you said.
And another question, Peter.
Yep.
That you talked about the mixing as you explained it as from observations. We know this, but it seems like that huge difference. Can you explain that just with a scale analysis, that there should be so little mixing across isopycnals?
Oh,
Really, just from observations.
it's observation, but you also, because the density, you have to do more work to actually get things across the isopycnals. So everything tries to work along the density, because that mixing requires less work. So
But will the theory then also give you this 10 to the 7th factor? Or?
oh, that's mostly from dye releases. And from analyzing the implicit mixing in high resolution models. So that 10 to the 7, maybe 10 to the 6, but it still works, because unless the sine of that angle is 10 to the minus 6, you're still doing, there are places in the ocean where the isopycnals slope more than that. So GFDL tried to put in, instead of horizontal diffusion here, they tried to replace the eddy parameterization with diffusion along isopycnal surfaces. So this was in the modular ocean model at the Geophysical Fluid Dynamics Lab. And this is just a technical thing, don't worry about that. So they tried running with this equation. However, in long climate runs, this model would fail, often near the Antarctic circumpolar current. And the way they made it continue was they went back to add in a horizontal diffusion with a coefficient that was an order of magnitude smaller than they'd used before, but it still had too much cross isopycnal mixing. So what the GM parameterization did was proposed that the effects of mesoscale eddies wasn't just a diffusive process, but it also produced an advection of temperature and salinity. So the difference between this and the last slide is that there's an extra advection of temperature and salinity, which we call the eddy-induced velocity. And we proposed a form, these are three-dimensional velocities here. We proposed a form which, just like the mean velocity, has 0 three-dimensional divergence. And we picked a form which was proportional, the vertical velocity is proportional to the divergence of grad rho over over rho z, which is the slope of the isopycnals. So where there's bigger slopes in the isopycnals, this quantity would be larger. And the reason we chose that form of the eddy velocity, because it mimics baroclinic instability and ensures a global sink of potential energy. So what happens in the ocean is where you either by wind forcing or other means set up slopes in the isopycnals, that kicks off this instability called baroclinic instability. And that tends to, if the slopes are like too steep or steep, then they tend to relax the slopes. So that is a reduction of potential energy. A minimum potential energy situation in the ocean is where all the isopycnals are flat and there's no motion at all. So GM, by advection, tries to reduce the slope of the isopycnals. And that mimics what this instability does. So we implemented this in a version of MOM at NCAR. And what I'm going to show you now is, this is a slide just to point out that if you've got a three-dimensional continuity equation like this, there's two stream functions, two-dimensional stream functions that you can generate. If you integrate over depth, then you lose because the vertical velocity is 0 at the top and bottom, and you have a balance here between du dx and dv dy. This is called the barotropic stream function, and it's measured in Svedrups. And it's a measure of how much water, depth-integrated water, is going round in the ocean. It's a measure of what's going round and round, so the wind-driven circulation. So for instance, you could say, what's the transport through the English Channel or the Straits of Miami? In the Southern Ocean, it's what's been transported probably through Drake Passage. And the ACC has a stronger transport in the horizontal than any other current. Estimates from observations across Drake Passage are something like 140 Svedrups. You can also form a two-dimensional stream function by integrating in x, where the x velocity is 0 at boundaries, or for the ACC, you integrate all the way around the globe. And you can have an overturning stream function, which tells you on average where water is going north and south, that's the v velocity, or up and down, and that's the w velocity. So things going north and down and back. So this is the overturning stream function. And that's the stream function that I'm going to show you now from some model results. So we ran a very low resolution, 3 degrees by 3 degrees, model that didn't have GM in it to equilibrium. And this is the final overturning stream function. So flow is going clockwise around positive contours here and anti-clockwise around negative contours. So what this is saying is that in the northern oceans, and this in fact happens nearly all in the North Atlantic, water is going north here. It goes down to about 3 kilometers, and then it starts coming back south. So this is called the North Atlantic meridional overturning circulation. Sorry, I'm not very good on this. So at the equator, there are more shallow overturning circulations, which are mostly closed. Down here, there's a circulation which is doing this. And this is that deep water is also formed on the Antarctic shelf, sinks, and comes north here. And this is called Antarctic bottom water, the densest water in the world's ocean. And you can see it slowly creeping north in all the 3 oceans, Atlantic, Pacific, and Indian Ocean.
Peter,
Yeah?
but the zero stream line comes all the way to the bottom at 45 south, right? So flow is parallel to the stream lines, correct?
Yeah, so this man, of course, knows too much. If you did this, this is actually an integral all around. If you did it for different basins, you would actually see a continuous flow around here. Or if you did it actually in density space, would be better.
So on average it's zero, but there's an exchange.
Yeah, there is exchange. But there's this quite strong here, overturning circulation, which is at the latitudes of the Antarctic circumpolar current. So what is happening is that in the Southern Ocean, you have these strong westerlies. The roaring 40s are blowing really strongly from west to east. This is pushing water in the Antarctic circumpolar current in the same direction. The velocities are from west to east. Coriolis force in the Southern Ocean, in the Southern Hemisphere, turns that to the left. So you have a positive meridional velocity that's directly wind forced in the upper ocean. That is closed by a cell which is not too extensive in latitude, but also goes down to 2, 3, 4 kilometers. So this is a positive cell like this. Now from that solution, we diagnosed what the overturning stream function would be from the Gent McWilliams eddy-induced velocities. And this was the answer. In other words, it would be rather small in most places. It would be a few flare-ups that would be positively enforcing this North Atlantic overturning circulation. But by far the biggest response is where the isopycnals are sloping the most. And that's in the ACC region. And as you can see, the sense of this is that the eddies would induce an overturning circulation, which is in anti-clockwise here, and would we thought it would not balance totally the mean flow, but would reduce it a lot. So this ACC, which is the only ocean current which goes all the way around the globe, is much more like atmospheric jets and so forth. And it's known in atmospheric jets that eddies, which are there defined as deviations from the zonal mean, in an overturning sense, act in the opposite way to the mean flow. And here we're seeing exactly the same in an ocean model where the big effect of the eddies would be to partially offset this overturning circulation in the Southern Ocean. So then let's try this. We did two different solutions to equilibrium. One where there was no GM at all, and we went back to horizontal tracer mixing, and one where we did it with the GM parameterization. And as you can see, in most of the ocean, this doesn't make very much difference to the overturning circulation, except right in the ACC, where this was the contribution from the mean flow doing this, and the eddies, in fact, in this simulation, almost exactly balance the mean. In all simulations since we've done that, this balance wasn't quite as good as this. What happens, though, every time is that the eddies, at least more than 50% or so, cancel out what's happening in the mean. Now, if you think about it, if you don't have this cancelled out, what this is doing is taking water from south to north. So this is taking cold water and bringing it equatorwards. So it does two things. First of all, that is up the temperature gradient. The temperature gradient is obviously warm to cold, and it brings cold water over warmer and lighter water. That means that the density gradient is then unstable because it's not positive upwards. And in these models, let's go back one, sorry about this. In these models, once the temperature gradient is unstable, they don't have vertical velocities, so they correct that by doing what was called convective adjustment. So you adjust the temperatures in the column until you go back to a stable density profile. And that, if the densities were almost the same all the way down, would then affect all the way from the surface to maybe 1 or 2 kilometers. And in the model, that was the mechanism to produce deep water formation. Now, in the ocean, deep water formation is known to occur in very, very few places. This is a sketch of what's happening in the North Atlantic. So you've got warm Gulf Stream water coming up. Convection happens in some years in the Labrador Sea, some years in the Greenland, Iceland, Norwegian seas here. This produces a circulation then, and as I called it before, it was North Atlantic deep water. Both the Gulf Stream and this actually hog the western boundary of the North Atlantic. But in that overturning stream function, you can't tell, because it's an integral in x, you can't tell exactly where it is, but they always occur on the western side. There is no deep water formation in the North Pacific because the salinities, it's not saline enough. In high latitude, salinities is the factor that's affecting density the most. And so in the northern hemisphere, deep water formation occurs in these places in the North Atlantic. Deep water formation is also known to occur on the coasts of Antarctica to produce that Antarctic bottom water. And because we can trace these water masses around, it's known that deep water formation occurs really only in those places. So what we did was we analyzed in those two runs, one using horizontal mixing, one using GM, where convective adjustment, so the model formulation of deep water formation was occurring. And remember that, this time I'll really do it, that this here is taking cold water over light. So the result is that in the one that uses horizontal closure, deep water formation is occurring a lot of the time in the Southern Ocean, just because of that overturning circulation across the ACC. And it's also occurring quite a bit in the North Atlantic. When you go to the GM formulation, the places where deep water formation actually occurs are reduced dramatically. And in fact, this is probably spurious, but that's our equivalent of the Labrador Sea, but generally in the North Atlantic, and also in two places off Antarctica, the Weddell Sea and the Ross Sea, which in fact are the two places that it's known that deep water formation occurs around Antarctica. So if you went to a sort of old-type grumpy physical oceanographer who went to sea and said, this is a representation of deep water formation, they would maybe agree with you. If you said this was the representation, they would say you're completely wrong. And really, it was this plot of where you were doing deep water formation that really told us that this parameterization put into ocean models for climate might have a really important effect on climate models. So, let's go back here again. Another thing that changed when we did this parameterization is that this overturning circulation in the North Atlantic transports quite a lot of heat polewards. The ocean and the atmosphere have to transport heat polewards. If there was no transport,